Okay, so over the last couple of days as we've started our new unit, we've been discussing the idea of action at a distance. Yeah, feel free, by the way, to move the desks a little bit if you can't see the board all that well. I have it bolded on this slide here, action at a distance. And this is really in contrast to what we consider to be the contact forces. If I push somebody or if I throw something, I know why it's in motion. It's because I literally came into contact with it, and therefore my action caused something to go into motion, right? But there are actually four fundamental forces that we know of in our universe that they occur with like there being a gap, a distance between where there's no direct contact. And we're actually going to cover these basically by the time we're done Physics 30. The first one you guys should know, it's gravity. We've already discussed this, right? Earth has a gravitational attraction to our sun. It's what keeps Earth going around in an elliptical orbit. Right? But does Earth ever touch the sun? Well, no, thank goodness. That would be horrible, right? Same thing with like you and I being attracted to the Earth itself. Although we are in contact with the ground, we can just lift something off the ground, let it go, and it will fall without there being contact. So that's one force. The electromagnetic force is the next force we want to work with, and that's more or less the focus of this unit. We're going to start in our first half of the unit discussing electrostatics, which is basically just talking about charged particles. But in the second half of our unit, we're going to discuss magnets, and we're also going to discuss the point in time where physicists realized that there was actually a link between the two, and that electricity and magnetism could actually, one could cause the other. Okay. Have you guys ever heard of something called an electromagnet? An electromagnet is where you run electricity through a wire and you make yourself your own magnet. They're kind of cool. It's also what leads to our third unit. Our third unit is on something called EMR, known as electromagnetic radiation. And so that's our goal basically this unit. There are two other forces that involve action at a distance. There is the weak nuclear force, and we're going to discuss this in our final unit. The weak nuclear force involves radioactive decay. So if you've ever heard about elements on the periodic table that are radioactive, and you've heard of things like half-life, many of you guys have done Math 30-1, correct? You might have discussed half-life in that course, exponential decay. We're going to discuss that. That's another force that occurs at a distance. The final fundamental force is something called a strong nuclear force. And to try to describe this, basically the idea is, imagine you have a nucleus of an atom. What is in a nucleus of an atom? Protons and neutrons, right? Now, protons want to repel other protons. And so logically, nuclei should actually, on their own, they should want to basically explode. Because if you have a proton here, and you have another proton here, another proton here, and you have all these protons next to each other, protons want to repel each other. In theory, all nuclei should want to basically explode apart. And some of them do. We call those fission reactions. They're known as nuclear reactions. But with the exception of uranium and plutonium and a few others that actually do undergo like radioactive fission, most nuclei don't break into pieces. And the question was, well, why? Here's the cool part. I love this about physics. Scientists don't really know why, but they know that there must be a force keeping nuclei stuck together. And they've called it the strong nuclear force. And yet we really don't know how it works or why it works. We just know that it must be working. Because if it wasn't, nuclei would bust apart. Does that make sense? Anyways, I'm kind of getting off topic because we don't need all of that information here. I just want to discuss the idea then of these action at a distance forces and these four fundamental ones. We're going to focus on the big three basically: gravity, and then electro/magnets, and discuss those forces. Today's topic then is the idea of a field. And you've probably heard this word before in Physics 20 perhaps. Maybe you heard the word gravitational field at some point before. A field, the technical definition would be right here. If I ask you this on like a lab, a field is defined as a 3D region of influence. Influence is kind of the big word. A field basically says if a particle was located here, here's where it would go. Okay? If a particle was located here, here's where it would go. Here's what it would do. Let me just draw you a quick picture here. Imagine this was the Earth. This is the Earth. Earth's gravitational field works like this. I would draw all sorts of lines pointing in towards the Earth. Why are they pointing in towards the Earth? Because gravity pulls everything together, right? So if I was on this side of the Earth and I jumped up into the air, I would get pulled that way. But if I was on the other side of the Earth, and I'm going to apparently draw the person standing on their head, because this would be on like the opposite side of the Earth, would this same direction still apply for that person? Well, no, because they'd get pulled like in a three-dimensional area, they'd get pulled the opposite direction, right? But that's the idea, is a field is a way of trying to like represent that as to like where would something go, what would it do? And this bottom little note right here is really important. A field is not a force. They are similar. They are highly related, but they're considered to be different from each other. We actually have unique formulas for each. A force is something measured with capital F, and it's measured in newtons. But fields kind of differ depending on what type of field. We have gravitational fields, we have magnetic fields, we have electric fields. Okay. So, this slide also talks about scalar versus vector. A scalar field could be an example like heat from a fire. If I were to draw just a basic fire here, which way might you draw this field? Well, maybe I don't really need to have a direction on this one because there's not really a direction on this. What I do know is that as I'm further away from the fire, like if I'm standing here versus I'm standing here, I recognize that this will be hotter than over here, but there really isn't like necessarily like a direction to temperature. Because like, do we assign a direction to temperature? You might argue, well, maybe the field goes outwards, but like heat and temperature are kind of different from each other. So there are some fields where you don't really have a direction to them, and there are some fields that you do need a direction, like there's a magnitude and a direction. So let me just show you this next slide, because I think I'm rambling here. Here's a classic example of how we would draw a field between some particles. This is a positive and a negative charge. And all of these lines right here are defined as field lines. That's what we call them, field lines. And so they describe what a particle would do when in this area. So like, for example, if you had a particle in this area right here, it would want to get sucked in towards the negative along this line of motion. If you had a particle over here, well, it wouldn't follow this same direction like that. It would actually go a different way, right? So this is how Faraday, this is one of the scientists we're going to discuss, this is how Faraday was able to explain how force could be transferred without objects touching. He described the fact that like even though these two objects were not in contact with each other, there was an influence. That's the word I want to use. There was an influence. And the influence is basically all these lines show you where things would go. Now, here's one of the problems. When they were trying to figure out how to define a field, they had to figure out whether to define it based on positives or negatives. We kind of had to choose. Remember the story about how, what's his name again? Lightning guy. Franklin. No, not that one. Benjamin Franklin. Remember how Benjamin Franklin had the lightning strike the kite that his kid set up, and he had to choose whether to make it positive or negative? Well, we kind of have to do the same thing with fields. We have to define a field basically on positive or negative. Look at this diagram right here. Does it appear like this diagram is describing what a positive thing would do or what a negative thing would do? Is this diagram describing what a positive would do or what a negative would do? Okay, let's try it. Let's say we had a negative. Would a negative want to get sucked in towards another negative? Okay. Or let's say I put a negative right here. Would a negative want to get pushed away from another positive? Okay. So it's actually the opposite. We define a field as what positive things would do if they were in this like general vicinity. So it's a hypothetical. Hypothetically, if there was a positive charge somewhere in here, all of these lines describe what it would do. Right? So if you put a positive proton right here, wouldn't a positive proton want to get away from this positive charge? Wouldn't it want to start going this way? But then wouldn't it start to become influenced by this negative over here? And it start to go, well, okay, I want to get away from this guy, but hang on, isn't there a negative over here? Whoop, I'm going to go do a loop over here. So that's what a field does. In electrostatics, we define a field as what hypothetically a positively charged particle would do at any location. And that's what all these lines basically describe, is where motion would take it. That's what I actually have written on this slide right here. What we do is we use a pretend test charge. We consider what like a hypothetical particle would do. And we always consider the source charge to be a positive. So I kind of have a fill in the blanks in my notes right here. Say we have a positive test charge moving towards an unknown source charge. What would the unknown charge be if it was moving towards? If a hypothetical positive test charge would move towards something, the unknown charge would have to be negative. Good. But if you had a hypothetical positive test charge moving away from a source, well, then that source must be positive. So what I've got on the next couple slides here is some pictures of fields. Okay. I'm going to go do this one. There we go. Here's one I want to use. This would be an example of like a field diagram, where what all these lines are doing is they're describing what hypothetically a positive particle would do in any location. So if you put a positive right here, what would it do? Well, it would want to get as far away, because there's a positive here, right? What if you had a positive charge right here? Well, it wants to get away from this positive, right? It also kind of wants to get away from this positive, and so its net direction would kind of go upwards. Right here in the middle is kind of a cool area. What if I were to put a positive right between the middle of these two positives? Where would it go? It would stay there. Yeah, you can actually see that like right in the middle right here, there's kind of like a gap where there's not as many lines. There's lots of lines over here, right? There's a line here and here and here and here and here. But in the middle, there's kind of a gap. If you put a positive in the middle, it would hover because this one wants to push it, this one wants to push, and like it would sit there. Let me go back and show some other slides that I've skipped here that are all involving like vector diagrams. This one shows fields for what a positive and a negative would do. So again, we're considering what a hypothetical positive charge would do. Say you put a hypothetical positive charge right about here. What would it want to do? Well, it would want to get away from this positive over here. But it might start looping around and want to get sucked into this negative over here. Or let's say you put a positive somewhere right over here. It's going to want to get away from this positive, but isn't it going to want to start looping around to this negative over here? So hopefully I've made my point well enough that all of these lines, they describe what hypothetically would happen if there was a charged particle, a positively charged particle, put in that area of influence. Does anyone have any questions on that so far? Did I skip this slide here? Yeah, okay, why don't we try this one right here? Why don't we draw these field lines right here? The field lines, well actually no, they're already drawn, aren't they? Never mind. Because we always draw field lines as though what a positive would do. So a positive would want to get sucked into a negative, and a positive would want to get repelled from another positive. So I think I probably already covered that well enough. Where's the diagram I wanted? Here it is. This is the diagram I was looking for. So this is something I want you guys to be familiar with, the idea of here's all of these lines going on here. I want to discuss which direction they're traveling. If this is just a single negatively charged particle, all of these are field lines. But if I were to ask you which way the arrows should be pointing, should the arrows be pointing away, or should all these arrows be pointing towards? Towards, yeah. Let's just cross that out. They'd all be pointing towards. That's how we would define this field. We just had to pick one. and they just randomly decided to go with a proton as what we defined a field as. Okay. Now look at this one right here. If we have two negatives, then this is going to want to get sucked in towards this, so all these arrows are getting pointed in there. This is also getting sucked in here. And here's where you have another cool area. Can you see how there's a bit of like a gap almost in the middle right here? What would happen if you put something exactly equal distance between these two particles? It would hover there, because it would want to get sucked towards this one, but it would also want to get sucked towards this one. There'd be like an equal tug of war, and it would literally, it would hover right there, which is kind of cool. In this next diagram right here, you would be drawing all of these lines towards the negative charge. And the reason why is that they'd be coming away from the positive charge. Everything that's positively charged wants to come away from the positive. And so, like, say you had an object that was over in this location, way on the far side here. It's just going to get pushed out, right? Everything on the far right-hand side of the screen is going to get pushed away, but some things are, say, going to get pushed down, and they would loop around and get sucked in due to there being like a second region of influence. I want to focus on this last one now. This is one of the coolest shapes. What if we could have a negatively charged ring? Well, all of these lines right here would be pointing in towards a negatively charged ring. What's going on in the middle of the ring? Well, in the middle of the ring, it's actually the same sort of thing as right here. It would want to be going this way, and this way, and this way, and this way, and this way. What if you put something right dead center in the middle of the ring? It would also just stay there. Yeah. Exactly. Yeah. Which is kind of cool. Yeah. There's a concept we're going to learn about later on in the course. It's called a Faraday cage. And I've discussed this earlier with you guys. One of the safest places for you to be in a lightning storm is in your car. And there's two reasons why. One is that the car's tires are rubber. They're insulators, so electricity can't go through the car. But even if it did, your car acts as a Faraday cage, because what ends up happening is the steel frame of your car ends up having an equal amount of electrical force. And what ends up happening is if you are in the middle of the car, the field is pulling equally in all directions because of the way that the car's structure is made. And so if you're in the middle of the car, there is literally no field there, because it's like it's equal distance in theory to all other places. And like those vectors, they cancel each other. We'll talk about this more later, but if you can kind of see that overlap between the circle here as well, if you're right in the middle here, it's a very safe place to be. All of these different lines right here, they would cancel each other, and you'd have a net of 0. Okay, let's get to the math part of this. There is a formula that relates a field to a force. Okay, they are not the same as each other, but they are very similar. A field for electric field is defined by this letter right here, capital E with the vector arrow on top. It has to have the vector arrow on top, because fields, we have to know which direction they're moving, right? Like clearly a direction matters for a field. A field going this way versus this way makes a difference, right? So this is the symbol for your field, and the way you calculate a field is you take the amount of force you have and you divide by whatever charged object is being used. Okay? So if you have like a test charge that is being attracted, Q is the charge of that object. That's how you calculate how strong your field is. One of the things I need to point out here is that E actually has two designations in physics. There is E as a vector, which is a field, and there is E, which is energy. And this is dumb. This is one of like I wish we could fix this. But you know how there's 26 letters in the alphabet? There's more than 26 physics variables, and some of them got doubled up. And E is one of the ones that got doubled up. E can be used for energy. E can also be used for a field. And the only difference between the two is whether you put a little vector hat on top of the two of them. So you have to be really careful when you use formulas that you don't think this is an energy amount. Okay. Let's try a formula, an example here. Let's say that we have a negative 7.94 Coulomb source charge. So I'm just going to draw a bit of a picture here. I'm going to have a negative 7.94 Coulomb charge. This is a negative charge. And we're going to put a positive 3.7 test charge 2.7 meters to the right of it. So over here to the right, I'm going to put my positive 3.7 Coulomb charge over here. Let's talk about the field lines for a bit, though. What would the field lines be doing to a negatively charged object like this? They'd be going towards it, right? So if it was over here, it would be going towards. Above would be towards. Here would be towards. Long story short, this object would want to be attracted inwards, right? What I'm asking, though, is try to calculate the field strength. Well, the formula that we just learned for field strength is the field strength is represented by this little capital E with the little vector arrow. I want to figure out how strong is this field in this region of influence right here. And the formula we use is that the force divided by your charge, that is what gets you your field strength. Well, we have the charge that we're using. The charge that we're using is this 3.7 charge. So this number right here could be 3.7 coulombs. Problem I have is, if you read the blurb above, I don't believe it told me how much force of attraction there was between these. However, in yesterday's YouTube video, didn't we learn a formula for the force of attraction between two objects? The force of attraction between two objects is K Q1 Q2 over R squared. Oh, you're right. Jeez, I'm so dumb. Here I was thinking that we needed to calculate it, and you're right, it says it right there. Never mind. Okay. I was getting ahead of myself. Hypothetically, let's say it didn't tell me this force right here. We could do a two-step question. Yeah. Sheesh, I was getting ahead of myself. Does this make sense where I'm going here, though? We could have calculated this force because I believe we know K. We know both Q values, and we know a radius. We could have solved for this force, and I guess it would be this value here. So I take it back. Let's do the shortcut. Just make this number be 3.62 times 10 to the minus. Is that 10 to the 10 or 10 to the minus 10? 10 to the 10. Okay. 3.62 times 10 to the 10. Divide by 3.7, and we'll have our answer. Thank you, by the way. That was a good catch. That saved us a lot of work. Okay, so 3.62 times 10 to the minus 10 times 10 to the 10 divided by 3.7. Okay, so has anybody else tried this? I got a 9. I got a field strength here of 9 point, I guess we got 2 sig digs. 9.8. What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9. Do you guys get that? Everyone who tried that? Okay. The units for field strength, by the way, are newtons per coulomb. However, there's one more thing we should consider. This is really ticky-tacky. It's a little minor detail. But this was a vector, so we should be including a direction to it. And so then the field at this location would be towards the left. At this location, the field was going towards the left. However, let's say you took this exact same object and put it over here. Then the field would be acting towards the right. Take that exact same object and put it above it, it would be acting down. Do you guys get what I'm saying there? But a field does require a direction. So let me just recap this one more time here. The formula is force over charge to give you a field. In this example here, I didn't even realize it, but I did give you the force and the charge needed. So that was pretty straightforward. But hypothetically, let's say that I didn't give you the force and the charge. What you would do then is you would use this formula here. You know K. I gave you both charges and I gave you a distance. You could then find the force, which should be this force right here, hopefully, and then divide by charge. So. Any questions on that first one? Let's try another one here. I've got a slide here that kind of discusses two formulas that are somewhat similar to each other. I didn't teach you guys Physics 20, but is this a formula that you guys are familiar with from Physics 20. Maybe not written this way, but did you ever see the formula Fg equals m times g? You've seen that formula, right? Well, you guys probably learned that gravity is 9.81 meters per second squared. I don't know whether it was discussed with you, but that is known as a field strength. That is the field strength of gravity. And so there's actually a very similar overlap between electrostatics and gravitational fields. The gravitational field means take gravity and divide by a mass. The electrostatic field is found by taking the electrostatic force and dividing by a charge. But there's a very similar concept in both of these here. It's related to mass in gravity, and it's related to charge in electrostatics. Now, on Earth, gravity's field strength is 9.81. But you guys know that it's not actually 9.81 everywhere on Earth, right? Like if you were to go to the top of Mount Everest, due to like a higher distance, like an altitude, I can't remember what it was. I think it's 9.5 or 9.6 is gravity's effect. The higher up in altitude you go. I don't recall it anymore, but hey, let's try this. Hey, Google, what is the amount of gravity on the top of Mount Everest?
On the website Florida.com, they say Everest is almost twice the height of Florida. Some actually say 8,840 meters above sea level. But as you rightly said, gravity has changes the altitude. The gravitational force is proportional to 1 by 2, where r is the distance from the center of the Earth.
This may not have worked.
The reason why slopes of the ellipse is 3
Well, that didn't work. I thought I was gonna get there. Okay, you guys have heard this though before, that like the higher up in altitude we go above the Earth, the less gravity there is. Okay. Well, the same thing kind of applies here. If you had a charged particle here, and I moved that charged particle further away, well, wouldn't the field be weaker the further away it is? So. Okay, let's try another example here. Let's say I give you a positive test charge, and we're going to put it in an electric field, and I'm going to tell you the strength of the field. Let's find the force. So I'm just going to draw a picture to kind of illustrate it first. I'm going to have a field, and the field is going outwards. So there must be some sort of charged particle that's causing a field to push outwards. What type of particle must this be to make an outward type of field? A positive. Yeah. Now I don't know exactly what this positive charge's value is, but I know the field is causing it all to get pushed outward. And somewhere in this area here, we have a little positive test charge getting pushed away from it, and it has a value of 3.7 times 10 to the minus 6 coulombs. I also know the field at this point. At this particular point in time, the field was 2.3 times 10 to the minus 2. So this is a pretty straightforward formula. Your field amount is equal to the amount of force you have over the charge you have. So if you want to figure out the amount of force exerted by the field, multiply by your charge. So E times Q will be equal to F. So 2.3 times 10 to the 3 gets multiplied by 3.7 times 10 to the minus 6. That's it. I got 8.51 to the minus 3. So that'll be 8.5 times 10 to the minus 3. And the unit for force, newtons. So I think I picked this example because I wanted just to illustrate the idea that are force and field related? Yes. But are they the same as each other? No. They actually have a direct relationship. If I were to plot the amount of force you have based on the amount of field strength, there is a linear relationship. If you have a stronger field, you'll have more force. Does that make sense? So they are related to each other, but the link between them is how much charge the particle has. If you have a bigger charged particle, it would also make a difference too. Any issues on that? Yeah, question. We probably should. I guess it would still be outwards then. Yeah. I mean, since it said the field was going outwards, then the force should be going outwards too. Yeah. No, whenever we use negatives in electrostatics, we almost always just ignore them entirely. Like when we have a formula like this, or especially the formula F equals K Q1 Q2 over R squared. If you have a negative charge, just ignore the negative, right? And just apply the negatives when you want to figure out whether it's going this way or that way, right? Okay. We can actually take some formulas and merge them together. And what I'm going to now do is I'm going to take this formula right here, the one that I've introduced to you that shows you how to calculate a field, the formula that we learned last day, and I'm actually going to blur them together, merge them. If you can kind of imagine, I'm going to take this FE right here and replace it with this FE right here. So through the process of substitution, take this whole piece and put it right there. You would then have E equaling K Q1 Q2 over R squared over Q. Can you see how I take this whole piece right here and plug it in right there? Well, if you do that, it actually gives you this formula here. And the reason why is that one of these charges can actually cancel. And this is actually somewhat similar to stuff that you've done in gravity as well. You might have seen this formula before, that the gravitational field strength is equal to big G times m over r squared. Maybe you've seen that formula from Physics 20. Same kind of concept here. So the way this formula works, though, and this is important to get the difference, though. If you're using this formula right here, there's only one Q value left to work with. The one that is left is the source charge. It's the one that's actually providing the field. So if you use this formula right here, the Q that you use is the one that causes the field, not the one that is in the field. Can I say that one more time? Because I really want to articulate those words. There's always two charges, right? Like when you have this formula here, there's always charge 1 and charge 2. There is a charge that is causing a field. That is the source charge. And there is a charge that is in that field. That would be called the test charge. So when you utilize this formula right here, use the charge that is creating the field. Let's try an example. Say there's a tiny metal ball with a charge. I want to know the magnitude and direction of the field it produces 30 centimeters away. Again, these are pretty low-level difficulty questions. You're more or less just plugging right into the formula. So E equals K times Q over R squared. We have all these numbers. K is 899 times 10 to the 9. Q is the charge that is creating the field, which is this one right here. Now, I know there's a negative, but do we even need to use the negative in front of this? No. I'll deal with the negative later. So I'll make this 3.0 times 10 to the minus 6. And divide by the radius. The radius needs to be in meters. This was in centimeters. I don't care how you convert it. I like doing this. I go 30 times 10 to the minus 2, because I know that's how you convert centimeters. But just don't forget to convert, and don't forget to square, by the way. A lot of students miss this squared sign for some reason. Okay, I got, with 2 sig digs, it looks like 3.0 times 10 to the 5. Anybody else get that? Who's trying this along? 3.0 to the 5? Okay. What are the units for a field again? Newtons per coulomb. Now, this is a vector field, though. This is the type of field where you need a direction, right? Now, like heat, again, heat was something where, like, if you give a temperature doesn't have a direction, right? But this field, we do need a direction. This is where the negative comes in. If we had a negatively charged object, does the field go towards the negative or away from the negative? Inwards, yeah. Because we just had to randomly choose something to be the designate, and so we just chose positives to be the thing that we consider it to be. So if this is a negative, the field would then be going inwards. It's probably the best way I could describe it. The field is going inwards. On your formula sheet, sometimes you'll see fields with absolute value signs around them. Are you guys familiar with the concept of absolute value in math? One of the reasons why we would use an absolute value is that even if a student did choose to put a negative in right here, even if they did put in a negative, we would choose to ignore it and make it the absolute value, because you should really never have a negative field amount. You should always have a positive field amount, but you tell me which direction it is, right? So we rarely consider the negatives until we care about the direction part. Okay, I think I have 2 examples left. Yeah, 2 examples left. One more simpler one, and then one that's like more of what you need to be ready for. I want to figure out the electric field strength right in the middle of these 2 charges. So equal distance apart. Well, which way would you draw these fields? Wouldn't this field be drawn in towards a negative? But wouldn't this field also be drawn in towards this negative? So if I were to put something right in the middle, isn't it getting pulled this way and getting pulled this way? Wouldn't a hypothetical object in the middle here be getting pulled in both directions? However, these 2 have different charges. So is it just going to hover there? No, it will actually move. I think we know it's going to move towards the red sphere, but we have to figure out like with what amount, right? So all we have to do is do this twice. We have to calculate the field in the first location, calculate the field in the second location, and then subtract them. So let me write this out here. It's going to be kq over r squared. It'll be kq over r squared. And I'm going to find out how much this first field is pulling with. I'm going to find out how much this second field is pulling with. And I'm going to subtract them because they're getting pulled in opposite directions, right? So k was 899 times 10 to the 9. Q is the source charge, which was 1.2. Ignore the negative. The negative doesn't really matter. And then since this was exactly halfway in between, it's going to be 0.29 squared because it was 0.58. So 0.29 here and 0.29 here for distances. So 899 times 10 to the 9 times by 1.2 divided by 0.29 squared. I have a value of 1.28 to the power of 11. I'm going to save that as letter A. And then just do the same thing over here. For the second field, I calculated a value of 4.16 to the 11. I'm going to store that as B. Has anybody else calculated those yet? You got the same numbers as me? Awesome. Okay, I'd like to show this here just to make sure I'm clear. I want you guys to know the concept of a free body diagram and a vector diagram. Those are words that you need to know. I talked about them in the video the other day. But if I were to draw a free body diagram of the fields in play, there is a field 2 going this way. There is a field going this way. And can you guys see how I drew them with different magnitudes? I drew this one bigger than I drew this one. So this would be known as a free body diagram. In case it comes up, you need to draw one of those. All you got to do then to find your net is just do E2 minus E1, which was B minus A, which is... How many sig digs do we get? 2? It's almost always 2. I got 2.9 to the 11. And the units would be newtons per coulomb. However, this isn't sufficient yet. Why isn't this sufficient? I need a direction. And the direction is that the net amount was pulling us to the right. It's really ticky-tacky. to miss that, but that's an important concept. Direction matters here. You guys have any questions so far? Okay, if I'm being perfectly blunt, everything that we've done so far, I don't expect you to be given questions on the diploma that are of that level of difficulty. Most of those are pretty like one-step plug-in formulas. This last example is something more that I need to prepare you for, though. A two-dimensional puzzle where you have to break things up into X and Y dimension type things here. Okay. Now, what I actually want to do for this last example here is I want to have you guys solve it, but I want to walk you through how we're going to solve it first. I won't do the math for you. I want you to try that, but I want to walk you through how you do that. What if I asked you for the electric field strength at point P right here? Before we do this last example here, let's talk about all the field lines again. Since this is a negatively charged object, we would be having field lines going in towards this negatively charged object. This would be a positively charged object, so they'd be going away from this positive object. And what ends up happening is they start to loop around. And so we would have something that looks something like this at this point right here. What we have to figure out then is, well, what is the magnitude and direction of the field at that point there? I think I know that it's roughly going that direction at that point there, but this is very similar to what we've been doing in momentum. It's very similar to what we've been doing so far in the lesson we did yesterday. We have to break this up into all the X and Y components. So let me walk you through how you're going to do it, and I'm going to have you guys try this last one. If I were to draw a line straight from A to P, hopefully you guys would agree that this line is supposed to be coming in like this, right? Because we draw lines towards this one right here. However, if I were to draw the line between P and B, it's going to be drawn towards P because we always draw things away from positives and towards negatives. If I were then to ask you about a free body diagram on point P, you would say that point P, I'll draw it with a box, has one vector that's pushing it this way, but a second vector that's pulling it that way. Does that make sense? That's your free body diagram. Well, we should really be breaking this up then into different like components. I'm going to draw a upwards red line right here, and I'm going to draw a sideways purple line. See how that works there? To do more colors here, why don't I try the other triangle? I'm going to draw a downwards green line, and I'm going to draw a, what's left? A sideways blue line. Can you guys see how there's 4 individual components we have to account for? Now, in the X direction, the purple and the blue are definitely like, it's going to go as a net in this direction right here. But we have to calculate who wins between the red line versus the green line. So we have to find those net amounts. And the way we're going to do that is something like this. You're going to have to find the field on the hypotenuse right here, and you're going to have to find the field on the hypotenuse right here. Then, to find green, green is going to be your field times by the sine of, is that 36.9? And that will give you, say, letter A. And if you take that same field, we should call that maybe field 1 perhaps. This will be field 1. If you take field 1 and times by cosine of 36.9, that will give you B. If you take field 2 and times by the sine of 53.1, you would get C, which would be this side. And if you did field 2 and times by the cosine of 53.1, you would get D. I'll call that side right there. Then you'd have to add B and D to each other. You would have to subtract A and C from each other. Use Pythagoras' theorem to get a resultant, and use tan inverse to get an angle. Does that process make sense? Okay, so I've kind of walked you through how to do it. I want to give you guys 10 minutes or so. Try this question, okay? I want you guys to try it, and then I will come up with the answer in a few minutes here, but I don't want to do it for you. I want you guys to try. If you're